Hello, today we're going to continue our discussion of radicals, and we're going to simplify some more radicals. As you can see, I've got two examples here for you. The first one, the square root of 16. I can go through and look at the square root of 16, and you might recognize the square root of 16 already. This is definitely a problem that you may have seen come up using the Pythagorean theorem or something. So I'll jump to my calculator and check out the square root of 16, and clearly the calculator tells me that the square root of 16 is 4. So with that in mind, I can just simply say the square root of 16 is 4. Alright, I don't need the square root of 16, just rewrite it as a 4. Let's try the 20 as well. So once again, I think I will look at my calculator and try to plug that in. The square root of 20 is, ooh, that's weird. That's a terrible little decimal, isn't it? 4.472, etc., etc. So why was this number so crazy when this one worked out so well? Well, the answer why this one is so crazy and this one worked out so well, this one is definitely what we call irrational. It's a number that goes on and on and on forever. It doesn't repeat itself. You can't write it as a fraction. Whereas this number ended up being what we'll actually end up calling perfect. And why is that the difference? Well, it ends up being nice because the 16 is a perfect square. Whereas the 20 is a non-perfect square. So before we go any further, we'd better remind ourselves what it means to be a perfect square. Perfect squares come from a pattern of numbers, and they come from taking any particular integer and squaring it. So 1 squared is 1. 2 squared is 4. I can continue the pattern and generate the rest of my list. 9, 16, 25. I can continue. And so on. This list does go on forever. Why are these numbers useful to me? Well, remember, these perfect squares are something that help you simplify radicals with a perfect square. And that's where we're going to focus our time on. Let's go back to the square root of 20. We know before that it's not perfect, gives us an irrational answer, but is there a way we can write it using a perfect square? And the answer is hidden somewhere in here. What we want to do is we want to rewrite the square root of 20. We want to know, do any of these perfect squares go into 20? And I think I recognize that 4 times 5 equals 20. 4 times 5 is 20, and 4 is a perfect square. We can take the square root of 4 times 5 and actually break it into two pieces. We can say it's the square root of 4 times the square root of 5 and separate those into two pieces. And that's super useful to us because, as we already know, the square root of 4 is perfect. The square root of 4 is the number 2. And the square root of 5 is not on this list, so the square root of 5 is not perfect. And we will leave it as 2 square root 5. As you can see by using the calculator, both the square root of 20 and 2 square root 5 give me the same decimal equivalent, so I know that they are the same. Mathematically speaking, 2 square root 5 is in simpler terms than the square root of 20 because there are no perfect squares left as a factor. Let's try one more example. I've got the square root of 18. Now, I don't recognize 18 as being a perfect square up here, and in fact I can check the calculator and it definitely is an irrational answer. But I do wonder, are any of these perfect squares a factor of 18? And the answer is yes. I can break 18 down into 9 times 2. 9 times 2 is 18. and 9 is a perfect square factor. Knowing that 9 is a perfect square factor, I can now separate those into square root of 9 times the square root of 2. And since the square root of 9 is perfect, I know the square root of 9 is a 3, but 2 is not perfect, so I will leave it as the square root of 2. A quick check on my calculator shows that those two do give me the same value, so I feel comfortable that I've simplified them. These are two super quick examples. Let me know if you have any questions in the comments. Thank you.